Hello everyone, welcome to the channel with the Yoga. In this video, we'll discuss the literature review for the selection of drive system for performance enhancement of electric vehicle. As an introduction, a vehicle propelled by an electric motor rather than a petrol or a diesel engine is called as an electric vehicle. Electric vehicles are mainly classified into three types. The first is the hybrid electric vehicle, second is the plug-in hybrid electric vehicle, and third is the full electric vehicle, which runs solely on electric drive system. The major components of an electric vehicle are the battery, motor, and motor controller. The government of India is planning to transition to 100% electric vehicles for transportation by the end of year 2030 and is promoting the mass adoption of an electric vehicles through the FAME, that is faster adoption and manufacturing of hybrid and electric vehicle scheme. Total electric vehicles sold till now are 2,80,988 numbers. Total number of incentives are 2,80,830 and total amount of incentive claimed is rupees 359.58 crores. Now need of an electric vehicle. Electric vehicles have become popular in short span of time. They are essential due to the rapidly increasing demand for transportation in India, where electricity is more cost effective than fossil fuels and petrol prices are among the highest. Electric vehicles attract consumers because of their key features, that is zero emission and environment friendly operation, fewer moving parts compared to the traditional vehicle, silent operation, lower maintenance cost, and excellent acceleration, etc. Now, challenges of electric vehicle. Although electric vehicles offer many advantages, they also face several practical challenges such as high battery cost, high electric vehicle prices, frequent recharging, long recharging time, short battery lifespan, need for performance improvement, cost-effective motor design, and intelligent control design. This literature review work will help to address the challenges in drive system for electric vehicles, and it will be helpful to propose solutions for improving their performance. Now, requirement of motors for electric vehicle application. As discussed, the motor is major component of an electric vehicle and is responsible for driving the vehicle. The motor performance directly influences the overall performance of the vehicle. This figure shows the desired output characteristic of an electric motor drives in electric vehicles. The hill climbing capacity of the vehicle is determined by the motor's maximum torque. The maximum speed of the vehicle depends on the motor maximum shaft rotation speed, and acceleration is influenced by the characteristic of the constant power curve. Now, literature review 1 is conducted for the selection of an electric vehicle drive system to enhance the performance of electric vehicles. According to the current market scenario, various EV manufacturing companies use different type of motors for different EV models. As shown in the table, major electric vehicles use motors such as induction motor, DC motor, permanent magnet synchronous motor, and brushless DC motor, most of which require the permanent magnets. Now, after review the major type of motors currently used in EV application, the advantages and limitations of each motor have been addressed. Based on the review literature, the electric motor is key component of an electric vehicle. If we consider the induction motor, the advantages of this motor for electric vehicle application include simple construction, high speed, high reliability, ability of operating in hostile environment, absence of brush friction permit the motor to raise the limit for maximum speed, and the higher rating of speed enable these motors to develop high output, low torque ripple and noise, then established converter or manufacturing technology, absence of the position sensors. Now, regarding the limitation of induction motor for EV application, it includes higher cost, complicated mechanism of controller than that of DC motor, presence of breakdown torque limits its extended constant power operation, stalling of motor at maximum current operation, less efficiency than permanent magnet and switch reluctance motor, flux weakening beyond the base speed after rated power capability. Now, if we consider the brush DC motor, the advantages for EV application include simple controller, ability to achieve high torque at low speed, torque speed characteristics suitable for traction requirement, motor speed is adjustable through varying voltage. Regarding the limitations of brush DC motor, limitations are bulky construction, heavy weight, low reliability, more size, expensive, friction between brushes and commutator restrict the maximum motor speed, higher need of maintenance due to the presence of mechanical commutator and brushes, lower efficiency than the brushless DC motor. Another type of the motor used for EV application is brushless DC motor. Its advantages include high efficiency and power density, longer life, low noise, high starting torque and no load speed, higher life because of the absence of brushes and sparking, easy speed control, small energy loss. And limitation of this motor include magnet is expensive and motors are costly, heavy weight, motors of high power rating are not available easily, coupling the motor with gearbox of the existing vehicle is tiresome and time consuming, it suffers from the limited field weakening capability, more complex controller than brush DC motor, maximum speed is restricted for an inner rotor type motor. Now next type is hub motor. So hub motors are prepared for light electric vehicles. It is the compact electric motor placed inside the wheel and is directly connected to the rotating wheel. It generates high torque at low RPM. Next type is permanent magnet synchronous motor. So these motors are useful for such vehicles that have to start and stop very often in slow traffic in cities because of the high efficiency at low speeds. It is possible to increase the power density of these motors by using high magnetic flux density permanent magnets. And last type of the motor is switch reluctance motor. So advantages of this motor are simple construction, fault tolerant operation, simple control, operate with extremely long constant power range, high speed operation capability, high torque inertia ratio, simple rotor structure without any magnet, winding, commutator or brushes. Then absence of magnetic sources on the rotor make SRM easy to control and insensitive to high temperature. Extended speed of 2 to 3 times the base speed is possible. Then cost effective, desirable flux controllable characteristic, outstanding torque speed characteristic such as torque speed characteristic of SRM drives match very well with the EV load characteristic. And limitation of SRM for EV application include it suffers from the torque ripple. Then acoustic noise is present because of the presence of torque ripple. Absence of permanent magnet imposes the excitation burden on the stator winding and converter, which increases the kVA requirement of converter. And as compared to the BLDC motor, per unit stator copper losses of SRM are higher and it reduces the efficiency and torque per ampere. Now, as a summary of this literature review 1, electric motor is major part of electric vehicle. Currently, there are different motors in use like induction motor, permanent magnet motor, switch reluctance motor, and brushless DC motor, etc. according to the type and use of electric vehicle. Literature review concluded that there is no single motor suitable for all electric vehicle application. All motors are having some advantages and some limitations for EV application. Now, for the selection of electric vehicle drive system in this research, the table presents a comparison of different motors commonly used in EV application. In the table, a score of high indicates the highest efficiency, lowest weight, and lowest cost respectively. Based on the comparison of efficiency, weight, cost, and constant power characteristic, SRM drives show strong potential to replace conventional motor drives. SRMs are gaining significant attention due to their simple and robust construction, fault tolerance, and excellent speed torque characteristic. However, their major drawback is high torque ripple. Now we'll discuss the use of rare earth magnet in electric vehicles. There are different type of rare earth magnet, including ceramic, alnico, selenium cobalt, and neodymium iron boron. Among these, neodymium iron boron magnets are heat resistant and are widely used in high output electric motors. They help in designing the motors with high torque density, high efficiency, compact size, and lighter weight. The International Energy Agency, that is IEA, predicts neodymium demand may rise 20,000 to 40,000 tons by 2030. The figure shows global rare earth production, where India contributes only 1% of total worldwide production. According to the Indian Bureau of Mines, India relies heavily on imports of rare earth magnet, primarily from the China. If China were to halt the supply of rare earth magnet, it could result in a severe shortage and unpredictable rise in cost. So this would significantly impact the cost of motors and electric vehicles. Therefore, there is strong need to find the alternative solution to conventional motors such as rare earth free machines or reduced rare earth permanent magnet machines. Now, there are various motor technologies that aim to reduce or eliminate the use of rare earth magnet. These include reduced neodymium magnets, ferrite permanent magnet, copper rotor induction motors, wound rotor synchronous motors, and switch lattice motor technology. As shown in the table, when comparing these technologies based on the peak power, peak efficiency, active material cost per kilowatt, and torque density, SRM technology emerges as a superior option for reducing the reliance on rare earth magnet in electric machines. Now, literature to review 2, selection of SRM drive circuit topology. The main purpose of conducting literature review 2 is to select a suitable converter and controller topology for the SRM drive circuit. Before that, we will briefly introduce the equivalent circuit and the basic equation of the switch related motor. The figure shows the single phase equivalent circuit of SRM. Equation number 1, 2, and 3 provide the expression for voltage, power, and torque respectively. The SRM is similar to DC series motor and it provides good starting torque. The torque is proportional to the square of the current. The direction of rotation of the SRM can be easily reversed by changing the sequence of stator excitation. If a separate excitation circuit is connected to the winding on the stator pole and rotor is driven by a prime mover, the SRM can operate as a generator. This SRM is suitable for four-quadrant operation when used with converter. Speed and torque control are achieved through the converter control. Now, selection of converter topology for the SRM. The converter acts as an interface between the DC power source and SRM, ensuring the optimal performance, efficiency, and safety in electric vehicle application. The converter plays a crucial role in the SRM circuit for various functions, including excitation control of the main phases, current regulation, bidirectional energy flow, voltage and power conversion, rotor position sensing and synchronization, minimization of acoustic noise and torque ripple, and ensuring the system protection and safety. As per the literature review, there are various types of the converter used in SRM drive circuit, including asymmetric converter, Miller converter, C-dump converter, R-dump converter, bipolar converter, buck-boost converter, resonant converter, etc. Among these, the standard type of converter commonly used for modeling an 8x6 pole SRM is the asymmetric bridge converter. Now, as per the literature review, asymmetric converter and midpoint converters are mostly commonly used for four-phase SRM. Based on the comparison table, considering the parameters such as the number of switches, number of diodes, regeneration capability, control algorithm complexity, fault tolerance, reliability, dynamic performance, and cost, the asymmetric bridge converter is found to be more suitable for SRM in EV application. According to the review studies, many researchers have demonstrated the superior performance of SRM for EV application when using the asymmetric bridge converter. Therefore, asymmetric bridge converter is selected for the SRM drive system. Now we'll discuss the selection of controller for the SRM. The controller is used to regulate the performance of the SRM. Speed control of the SRM can be achieved using various types of controllers, such as the proportional integral controller, hysteresis controller, PWM controller, self-tuning adaptive control, fuzzy PI control, ANFIS, that is adaptive neurofuzzy interface system, and sensorless control method, and other self-tuning techniques. As per the literature review, the most widely used control methods for the SRM in EV application are direct instantaneous torque control, constant current control, constant flux control, and hysteresis control. The direct instantaneous torque control technique is used to minimize the torque ripple. In this technique, torque is directly chosen as the control parameter for switching the SRM converter. The constant current control method is widely adopted in SRM drives due to its simplicity in developing the torque. In the constant flux control method, the flux can be controlled independently of the current. Hysteresis control, also known as chopped current control, is used in the SRM to maintain the phase current within a band around a reference value. Current chopping can be easily implemented with an asymmetric bridge converter. So, as a summary of the literature review, the controller plays a crucial role in regulating the performance of the SRM. Various types of the controllers are used in the speed control of SRM. Researchers have reported improved performance of the SRM using the hysteresis control, particularly for light electric vehicles. So, hysteresis control method can be easily implemented with an asymmetric bridge converter and is therefore proposed as a solution as a suitable control technique for SRM in EV application. Now, these are the references that were consulted during the research work. So, if we consider the conclusion of this literature review, there are different types of the motors for electric vehicle application. SRM is also have fulfill all the requirements which are needed for the electric EV application, but still it is having very limited use for the electric vehicle application. If we have to consider the converter for the SRM for EV application, we can propose asymmetric bridge converter, and for the controller we can propose hysteresis controller for SRM which can be used for the EV application. Hope this presentation will be helpful for the researchers who want to continue their research in electric vehicle for the development of drive system for an electric vehicle application. Thank you.